Because we're using this one very nice relativistic effect, the Shapiro delay, it's a very, very clean measurement. And by clean, I mean you can actually see it in the data. It's not some incredibly tiny effect that we have to tease out. I mean, you would with previous generation of instruments, but with these new instruments and these new measurements with the GBT, it comes out strikingly well in the data. You can actually see this extra delay. And so because of that, it's a very clean measurement. You don't need to take data from many years. Our data were taken over basically 1 week of observing. That removes a bunch of other systematic effects that have plagued other mass measurements in the past. It's pure general relativity that people have worked out in very great detail and tested in great detail before. The reason why we've been able to do this now, because this pulsar has actually been known clear back since 2003. So it hasn't just become the most massive pulsar, it's just that we've happened to be able to measure that now. And that's because we have the Green Bank telescope, which is one of the largest telescopes in the world. It's 100 meters in diameter, and that gives us tremendous amount of collecting area. And these pulsars are incredibly faint sources, so we need as much sensitivity as possible. So if we get a big collecting area, a big bucket to collect all these photons, that's going to give us much more sensitivity. And then the second thing is the fact that we have a spectacular new instrument called GUPPI, which Paul has done a lot of work on.
GUPPI actually stands for the Green Bank Ultimate Pulsar Processing Instrument.
It's an excellent name, by the way.
It is an excellent name. So GUPPI is the part of the system that actually records the signal. It records and processes the signal that comes off of the telescope. So the telescope collects all these radio waves coming from the pulsar, focuses them down onto a single point. The signal gets converted onto a signal going along a wire and eventually ends up in our what we call our back-end system GUPPI. It's a rack of several computers that samples the signal at a very high rate, and it applies some specialized processing to give us the sharpest possible pulse measurement, the most accurate time of arrival measurement we can make of the radio pulses.
We are able to very precisely measure the arrival times of the blinks of the pulsar.
The reason why we're able to make GUPPI now is it's hugely dependent on very, very high performance computing and high performance signal processing.
We've taken cards that go inside your computer that are usually used for producing the graphics you see on your screen. We've reprogrammed these graphics processing cards to, instead of producing graphics, to process our pulsar signal for us. If you had a high-end gaming system, you might have one of these cards in your computer.
There's actually 8 high-end gaming systems in a rack, and together they do about 1 trillion operations per second, what's called a teraop. And to do that in real time basically has only been possible this year with these GPUs, because a desktop computer can only do a couple gigaops, which is a couple billion operations per second. So this is about roughly 1,000 times more processing power. GUPPI is the absolute world state-of-the-art instrument. There's a couple other groups around the world who are building instruments that are similar to that, and they're starting to get results now. But GUPPI is certainly the one that's in production use now. This is the first real great science result, in my opinion, that's coming out of these systems. We finally have enough computing power in real time to be able to do this, and that's why GUPPI works now.
So it's pretty interesting that pulsar astronomers, or scientists in general, are able to sort of take these technologies from gamers, essentially, that are developed elsewhere, and use them for cutting-edge science.